Welcome. This is the second question for AQA AS Unit 1 Physics 2009 past paper. Okay. So to kick off question 2, it's quite a common question to do with the strong nuclear force. Okay. Now I must quote that the strong force acts between hadrons, okay, with a strong nuclear force act between the nucleons, okay. Oh, anyway, so it's asking about the variation, basically how the separation between two nucleons affects the strong nuclear force. Now the graph looks, you may have seen it. Basically, we've got it's obviously all the way up here. It's repulsion. Okay, and below this axis, okay, which is the separation, we've got, okay, so just label that X, and it's in femtometers, which, just to put in your mindset, is 10 to the minus 15 of a metre, so very small. And down below we've got attractive, okay, and the graph looks something like that. In other words, what you need to take away is up to this point, okay. So between 0 and, so there's a couple of things you need to state 3 marks. The first mark is you need to state that between 0 and 0.5 femtometers, okay, it's quite clearly a repulsive force, okay. However, between 0.5 and 3 femtometers, it is obviously quite clearly very attractive. It's a very attractive force. And then the next point you would say is after 3 femtometers, it kind of goes out of range and kind of dies down. In other words, after 3 femtometers, all you need to state is it goes out of range. Okay, so that's quite a common question. It's just a case of learning that. Then 3 points about. So the difference is the 0 to 0.5, 0.5 to 3, and greater than 3. And you always need to state the conversion from femtometers into meters, just so the examiner knows what you mean. Okay, but it's quite an easy thing to remember. Okay, 2b part 2. 2b just says an unstable nucleus can decay by the emission of an alpha particle. State the nature of an alpha particle. Now, it's kind of a bit weird because it says, well, what actually is it? Now, there's 2 possible answers for this, and obviously, as with physics, they both mean the same thing. Okay, it's just a different way of expressing it. One way, and I think it's the most obvious, is that it has so 2b part 1, okay, it just says 2 neutrons and 2 protons. Okay, so actually I'm not even going to bother doing the second explanation because it's just a case of knowing that, and you can obviously look on the formula sheet for the other answer, but I don't think it's really relevant. It's just a case of knowing it's 2 protons, 2 neutrons, and obviously you can state that it has 4 nucleons, but really you've already stated that there. Okay, the next bit, the next 2b part 2, well, it's given us the start of an equation. Okay, so it's 238, the uranium-238 92 decays into thorium, but we're not told what the nucleon and proton numbers are, but we are told it decays by emission of an alpha particle, and obviously you know that's got a nucleon number of 4 and a proton number of 2. Okay, so then in case it's just, because obviously the numbers have to balance, it's very, very easy. Well, on this side we've got 4, and on this side we've got a nucleon number of 238, so obviously thorium must be a nucleon number of 234. And then we need to compare the proton numbers. We've got 92 and then that 2, so obviously thorium must have a neutron number of 90, and that is your equation. So it's just a case of working backwards, really. Okay, now I do say for some bizarre reason, if you didn't get the alpha particle, right, in terms of you just said it was, I don't know, 4 protons and 2 neutrons or whatever. If you assume that and carried it through, okay, correctly, as you would have assumed it, okay. Say if you did 4, I don't know, getting a bit confusion. If you didn't get the right structure of the alpha particle, but then you would have wrote that structure in this equation, you still would have got the marks for it, okay. But it's kind of crucial that you do understand that an alpha particle has got 2 neutrons, 2 protons, obviously, therefore a nuclear number of 4 and a proton number of 2, obviously. Okay, so that's 2B part 2, so quite an easy question so far. And the next one gets a little bit easier. Result, maybe I'm just saying that because I'm in the second year, so it is fairly easy. But anyway, maybe just being an arse as well. Probably quite likely that. Anyway, so for 2C, we've told this little bit of information that the uranium-238 decays in stages by emitting alpha particles and beta minus particles, in other words, electrons, eventually forming Pb, stable isotope of lead, 206. The first part, 2C part 1, just simply asks us state what is meant by isotopes. And it's just a case of realising, well, if it doesn't come to you straight away, then you should be thinking, well, what can I build myself up to? Stop bench pressing the table, obviously. Although, in the exam, if you truly have nothing else to do, just start doing that. And, I'll just go start lifting up other people's tables as they're writing on the exam. But don't say it came from me, because, it's not a revision tip I would definitely endorse. Anyway, moving aside from reckless teenage antics, okay? What I'm trying to say is building up to isotopes, okay? So, if you're not 100% sure, well, what is an isotope? If we just think, well, what are isotopes that I know? And this is very weird that you might know this and not know what an isotope is. We think, well, isotopes, well, I think uranium-239 and uranium-235. Well, if you look on the table, okay, you will see they both have a proton number of 92. So all that changes is this nucleon number. So if the nucleon number is the only thing that changes, but the proton number stays the same, then an isotope, therefore, is an atom with the same number of protons but a different number of neutrons. Okay, so hopefully that makes a little bit of sense. Okay, but if it doesn't really matter. All you just need to say is that an isotope is an atom which is the same number of protons but a different number of neutrons. If you wanted to sound really intelligent and make yourself seem like an arse, then by all means do, and you could just simply say it's got the same proton number but a different nucleon number. Or the examiner might think, that guy's being an arse, I'm going to deduct him a mark. So it's up to you if you want to risk your whole physics career, but I'm not bothered. Okay, so it's the same number of protons but a different number of neutrons. Okay, so very, very simple statement, just one of the things you need to know. Now this next bit, I didn't read the question right when I first attempted to do this, and I must be honest, I'm a bit of a prat. But anyway, it says if there are 8 decays in the involved in a sequence of decays from uranium-238 to this isotope of lead, which has got a nucleon number of 206 and a proton number of 82. Deduce how many beta minus decays are involved. Well, the first thing we need to do is, well, let's just have a think about, okay, so what we're going from here. We're going from uranium-238, which has got obviously a nucleon number 238 and a proton number of 92, and we're going to decay into a isotope of lead, so 206, 82. So it's got this isotope of lead, it's got 206 neutrons and protons and 82 protons, so quite clearly the difference between the two is how many neutrons we have. Anyway, so it says it decays by 8 alpha. It goes through 8 alpha decays, and we're asked how many beta minus decays are involved. Well, the first thing we need to do is work out what effect does having 8 alpha decays have on uranium-238. Well, we know that obviously an alpha particle has a nucleon number of 4 and a proton number of 2. So basically what we've got to do is remove 8 of them particles from uranium-238 and then see how many, therefore deduce how many beta minus decays we need to get from whatever that ends up being to this isotope of lead. So the first thing we need to do, quite clearly, is work out what effect removing 8 alpha particles has on uranium-238. Well, in other words, you can just simply times it by 8. Okay? So obviously, this isn't going to be, it wouldn't be a proper alpha particle, but I'm just stating it for ease of use or whatever. 8 times 4, well, that's quite clearly 32. Okay, so make sure I use 32, not going crazy. Yeah. Sorry, I'm just making sure I'm not going crazy. I do that every day, but yeah, not going crazy. Okay, so it's 3216, and that is basically, I know that's not an alpha particle, but you must think of it as what we're taking away. So if we take away 3216 away from 23892, what we get is obviously you take 32 away from 238. Well, that gets you 206. Okay, so that obviously we don't need to change the nucleon number. But when you take 16 away from 92, what we end up with is 76. So basically, at the moment, we've got, I'll just call it this atom X. This atom X has got 206 protons and neutrons and just 76 protons. Now, that's what uranium is after 8 alpha decays. But it tells us we obviously need a series of beta minus decays to get from this this X atom. Now, you don't have to draw it like this, obviously this is just trying to help you understand it. We need to have a certain amount of beta minus decays to get us to this isotope of lead. Now, the only thing we need to change here is obviously the proton number, because beta minus just affects the number of protons in a nucleus, because in beta minus decay a neutron turns into a proton. Okay, in other words, we increase the number of protons. So how many protons? Because anyway, let's just think of, well, what is a beta minus particle? In other words, it's B minus, so it's got a neutron proton number of 0 and a proton number of -1. Okay, that's how many it's leaving if you think of it like that. Okay, so how many -1s do we need to get from 76 to 82? In other words, what's the difference between them? Well, obviously the difference is 6. Okay, so therefore, because when we do, and this is probably not making too much sense, but I'll just draw what we've got so far. So 238 and 92 is what we started with, and then we went through 8 alpha decays, okay, to get us to this X element here. And what we've got here is this X element, okay, with 206 and 76, and we need to add on a certain number of beta minus decays, okay, to get to this isotope of lead. Okay, so basically, hopefully this makes sense. Because these have got to balance, okay, this maybe isn't making the best of sense. Yeah, it's probably not. But anyway, hopefully it does. It's like a double negative if you think of that. Anyway, just ends up being 6 decays. Okay? So if it decays, basically what's happening is a neutron's turned into a proton. So, in other words, how many more protons do we need? Okay? How many more of these neutrons do we need to turn into protons? In other words, how many more decays do we need? In other words, we need the proton number to increase by 6, so therefore we need 6 decays. So hopefully that's kind of... I mean, maybe I made that question more complicated than it needed to be, but anyway, I've just wasted some of your life. Okay, so thanks for watching. That's the end of question 2. I'm not going to do any fancy antics at the end of this one and do some other crazy little bit of extra knowledge that I couldn't be bothered doing in another video. That'll come later on, so don't worry about that. Okay, so thanks for watching. Hopefully it's been helpful. See you in the next video.